All right, so this is 125, and the CISSP class, and today we're going to just continue and finish Chapter 3, Security Engineering. And it's mostly cryptography and then some physical security. So, let me get this thing fitting on the screen, more or less. That'll probably do. All right. So let's talk about cryptography. And it is traditional to do it historically because the old systems actually never really die. They're not strong enough to use for many purposes, but the variants of them continue, and the pieces of them are reused in the modern system. So the old Spartan Scytale was one of the system where you just rearrange letters. You would write a message here, and then you would unwrap this tape, and so now it would be, the letters would skip like every fifth or sixth letter. This is a transposition cipher where you don't change any letters, you just change their order. But the idea was you would have to have another stick of just the same shape to decode it. The Caesar cipher, used in ancient Rome, of course, where they just move everything forward a couple letters in the alphabet. So an A will turn into a D, and a B will turn into an E, and so on, which will scramble things. That's interesting. Vulture has been probing your network. Yeah, I would imagine many of these cloud providers, Amazon hosts a lot of malicious servers too. A lot of people use these cloud servers for attacks, and they're CNC servers. It's a perennial problem. So the Vigenere square is where the problem with the Caesar cipher, it's easily cracked by frequency analysis. You can because every E is turned into the same letter, so you just count the most common letter, and that's probably E, and the next one is T, and so on. So if you have even a few paragraphs of stuff encrypted with the Caesar cipher, it's very easy to decrypt. So to prevent that, you can use the Vigenere square, which is probably French, and I don't know how to pronounce it, but you have a keyword. And so you use the T alphabet sometimes, and then you use the I alphabet and the M alphabet. You have a keyword which you repeat over and over. So it's a series of Caesar ciphers used. So the first letter uses one cipher, the next letter uses the next cipher, the next letter uses the next cipher, and so on. So it makes it more resistant to frequency analysis. This is called a polyalphabetic cipher, where there are several substitution systems being used. And here's a cipher disk. We used to hand these out in like cereal boxes when I was a kid. You just rotate one disk, and you now can get a translation from the outer ring to the inner ring. And the Confederates used it in the Civil War. They had the same thing there, so they could run the Caesar cipher. Then there's book ciphers, where you just use a book. You have to have exactly the same book at both ends. And then you just refer to the page, paragraph, and word, and then you pick out words in the book. And so these numbers are not mathematically translatable back to the original words at all. You just have to guess the book. But usually you choose a book that's fairly common, and it's not that hard to guess, and that's how that's cracked. Then there's running key. Like I said, this one I was describing, you use you use a phrase or document as the key, where instead of repeating just one word, like you might for the Vigenere cipher, you now take, say, the whole Constitution, we the people here. So you have a pattern of letters that does not repeat for a really long time. And then you use the W Caesar cipher here, and the E Caesar cipher here, and the T Caesar cipher here. And that's pretty good. And again, like the book cipher, the only way they're ever going to get in is by guessing what document you used as the key. So if you used a really famous one like the Constitution, then they might be able to guess it. Then there's code books, which were originally used just to save money on telegraph transmission, been around for a while. You just use code words for people, like, the Secret Service uses code words for the family, and people that sell drugs use code words for drugs to try to make it less obvious what they're doing on the telephone, and so on. You just replace a concept with a word. And then there's the perfect encryption system. It's been known for centuries. It's the one-time pad. It is completely unbreakable. No one has ever found any way in. It seems extremely obvious that there never will be any way in. You have a pad with pages full of random letters. And then you use each page only once. You never repeat anything. And so every letter is encrypted with a random letter off the pad. And therefore there is no pattern at all in the ciphertext. And what's worse is you could try to decrypt it with a brute force attack, trying all possible pads, and you would create all possible patterns of letters. So you'll create a whole bunch of messages that are readable, and you have no idea which one is the correct one. So No, the YubiKey hardware tokens are not a one-time pad. They are a pseudo-random sequence based on a seed number. That's what the Google Authenticator is, and I'm pretty sure it's the same thing there. And so they are a mathematical imitation of a one-time pad, and so is AES, a mathematical imitation of a one-time pad that is not as secure. But the problem with the one-time pad is the key distribution is horrible. You have to somehow, before you start sending messages, you have to somehow distribute a block of one-time pad to the recipient, which is more than the length of all the total messages you will ever send. And that is almost impossible to do, which is why this is almost never used. It's perfect, but the key distribution is so burdensome, it's essentially impossible. So what people use is something like AES, where you transmit a key that's only like 256 bits, and then you use that to generate pseudo-random numbers, which are like this, but there really is a hidden pattern. It's not as perfect. So Project Verona, the KGB used one-time pads, but what happened is the key distribution system got them. They didn't have enough one-time pads, so they started reusing one-time pads and making more than carbon layers. They'd make five or six copies of the same one-time pad. And the problem with the one-time pad is if you use it more than once, it becomes extremely easy to crack. And people were doing it last semester in my cryptography class. You can do it without a computer. The whole thing is ruined if you use the one-time pad twice even. It shatters like glass. So it's great, but only if you follow the rules, and the rules are too difficult to follow, so it's almost never used. So then they made these machines that will automatically, before we had electronic computers, they had mechanical devices with gears and such that would perform these translations as you type in. The Nazis had them, the USA had them, and the Japanese had them. And you'd type in the message, and it would have some dials you turn to put in the key, and it would automatically perform these translations. So then we had laws to try to stop people from exporting strong cryptography so our enemies would not have it. And this was to control export to Iron Curtain countries, and the Wassenaar arrangement in 96 is what finally relaxed this. So people that were into computing in the early 90s used to know that you could not distribute modern computers, and you could not distribute Windows XP to other nations if they were on this list, because it had the ability to do strong encryption, and that was forbidden. So it was quite a problem, and they finally knocked it off with the Wassenaar arrangement. Of course, I must say this is ridiculous, because cryptography is a matter of mathematics, and I think anybody can tell you that the Russians and the Chinese are no slouches at all about mathematics. It is ridiculous for Americans to say, we know math and they can't figure out math. It's more the other way. So pretending that they can't figure out a mathematical cryptography system is ridiculous. Anyway, so here's the basic types of cryptography. The one kind that's been around for millennia is symmetric encryption, where you have a secret key to encode the message, and the person you're sending it to has to have the same key to decode it. That's the only kind that's ever existed until 1970 in public sphere, when asymmetric encryption was invented, where you do not need to share the private key, which is enormously important because that was the key distribution problem, which is difficult. If you have some secure way to transmit the private key to the other person, why don't you just send your message through that secure method? Why are you using encryption? Distributing the key is a problem, and with asymmetric encryption, you don't have to distribute the private key, which is a brilliant idea. And a third technique used is hashing, which just puts a fingerprint on a file. You combine all the bits to make a fingerprint, and now you can just tell if that file has been modified. It does not transmit a message. It does not provide confidentiality. It just provides integrity. You can now tell if something has been altered because the fingerprint will no longer match. So symmetric encryption is the secret key encryption. This is the standard thing. There's many systems. There's strong ones and weak ones, but they all rely on somehow delivering the secret key to the recipient. So you do have to have some kind of trusted channel to deliver that secret key over, and that is a fundamental problem. There are stream ciphers that encrypt the bits one bit at a time, and there are block ciphers, which take a block of data and encrypt one block at a time. It used to be 64-bit blocks. Now the modern AES uses 128-bit blocks. So as we'll see, if you just do block ciphers alone, encrypting each block independently, there is a weakness in that system in that large-scale patterns in the input are preserved in the output. So to prevent that, you have an initialization vector and chaining. The initialization vector is a random value added to the plaintext before encryption, and then chaining uses the result of one block to change the next block, so that even if you have a block of input data that is all the same, the output is not all the same. There's a random or changing value, not really random, added to each block to make it different. DES was the original standard recommended by the US government and used through America through the 70s, 80s, and 90s, I think. Not quite sure when it started. And this came from an IBM algorithm called Lucifer, which had a 128-bit key and would have been very strong and uncrackable even now. But the DES, the government shrunk that key to 56 bits without explaining why. And the general explanation everyone believes is that this is because the NSA could now break it. That NSA's goal has always been not to let us use strong encryption that nobody can get in, but to design a system that has the property no bus, nobody but us. So the NSA can get in, but nobody else can get in, which is very difficult and has led to an awful lot of problems. So however, DES defined the basic modes in which to use it, which are just ways to handle it when your message is longer than a block size. So electronic codebook is the simplest, and all the rest of these amount to about the same thing. So electronic codebook is where you don't have an initialization vector and you don't have chaining. You just take every block of input data, like 8 or 16 letters, and you encrypt that. Then you take the next block of 8 letters and encrypt that, next block of 8 letters and encrypt that, all with the same key, and that's your encryption. Very simple. The problem is, if you take something like an image like this that has a block of green, then this is many 64-bit patterns of green, so they all encode to the same color. So as you can tell, this encryption has not really hidden the meaning of that image at all. This is not what you expected to do with encryption. You expected encryption to scramble it so I can't see the apple anymore, and it doesn't do that because each input block is encrypted independently, and repeated input blocks all produce repeated output blocks. That's why you use these chaining methods. Cipher block chaining mode adds a IV to the first block and then takes the output of that as the IV for the next block, and the output of that is the IV for the next block, and the IV keeps changing, so even this region that's all white turns into just random snow. This is what you expect encryption to do. Take the image and scramble it so you can't see the image anymore. That was like the whole point. And all these techniques will result in the same kind of random-looking snow. They only differ in how they choose the varying value to add to each block. All right, so single DES was the original implementation using a 56-bit key, and people began to complain in the 80s that that wasn't strong enough, and by 97, they actually cracked one, trying all 2 to the 56 keys became possible. Oh, is that similar to steganography? No, I'm glad you asked the question. This is just encrypting an image. Now, steganography is hiding extra data in this image. So you could change these colors in a small way so that you can't see the difference, and you could hide another message inside here, like a text message inside an image. That's steganography. And the thing about steganography is that you don't even know the message exists. You see an image, and unless you know where to look, you don't even know that there's a message hidden in there. It's not encryption exactly. What it is a covert channel. A covert channel is a secret transmission where you don't even know the transmission has taken place. Encryption is where you scramble a transmission, and people can look and see that you're sending a scrambled transmission, but they can't open it. So they're both used for types of secret messages, but that's the difference. Anyway, so DES is no longer considered secure. It was proven in 1997 that people could try all of 2 to the 56-bit keys, and therefore they could crack any DES encryption no matter how you choose the key, and that was pretty much the end of it. So, however, there's now a whole bunch of hardware designed for single DES out there in the world, being used at banks and industries and everything. So as a temporary measure to aid the transition, they invented triple DES, where you use 3 rounds of DES encryption using 2 keys, typically, and this ends up to make the effective key length 112 bits, which is very strong, and also it's very easy to turn it into single des if you want to, if you wish to continue using single des for a period while you're waiting to retire all your old hardware. This turned out to be secure enough, but in fact less efficient than AES, which is the modern replacement of DES. IDEA is another one, and this was patented. It has 128-bit keys, considered plenty secure, but it's encumbered by patents and slower than AES, so it's not very popular. AES is the main one. The main symmetric encryption used everywhere in the world today by all American products, recommended by the U.S. government. It's very efficient. As far as anybody knows, it has no significant weaknesses, and so it has a key of 128, 192, or 256 bits, all of which are very strong. Nobody's getting in there without the key, as far as anybody knows. And it's based on a mathematical algorithm called the Rinjale algorithm, I think named after its developer. And the way the NSA does this is NIST did. They advertise a contest saying, we're going to choose another algorithm, here's the rules, and then mathematicians and companies submit ideas, and they spend years competing to hack each other's products, and the ones that nobody can hack become finalists. Here are the finalists for AES, and therefore anything on the finalist list is a very good cipher, which nobody could crack. So you could use any of them, but they pick one of them and give it the stamp of approval and make it the U.S. government recommended one, and that was Rinjale. They took Rinjale and they turned that into AES, the Advanced Encryption Standard defined by NIST. So it's the one officially approved by the government and the military that the USA recommends use. But if you, for some cynical reason, might imagine that you do not trust the U.S. government, then you would use one of these runners-up, which have been proven very exhaustively to be very secure, but just were not the one chosen to be the best one by the government. So those are all perfectly fine ways to do things, but if you choose a non-standard one, then if you're planning to sell your product to the military or the government, they probably aren't going to like that. So that would be your issue. And so the way AES works is you take blocks of data, add a round key, and then you just substitute bytes, shift rows, mix columns, and add a round key, and do that 9 times, and then the last time you only do 3 of the transformations. So that's what I said. Those simple things, like the Caesar cipher and such, are the fundamental transformations, and you just combine them in a different combination to make AES. But this carefully chosen series of steps turns out to be extremely strong, and also it's designed to be extremely fast on modern computer hardware. They choose transformations that you can do on a computer quickly. All right, Blowfish and Twofish are ones developed by the famous cryptographer Bruce Schneier. You can see him at RSA and lots of other conferences. And he made it so it has various key sizes so you can test various levels of encryption for mathematical and cryptanalysis purposes. And they didn't win the contest, but they're considered good. RC5 and RC6, these all come from R is Rivest, Ron Rivest at MIT. His group keeps making cryptographic things, and so they made RC5 and RC6 that are both considered, again, quite strong, but they were not chosen by the government as the official AES. So then we get to asymmetric encryption, the new one. This was a U.S. Classified military secret for about 20 years, but then eventually someone reinvented it on the outside, I think in 79. 77 here. Anyway, so this is, so here's how it works. Each person has to make 2 keys. You make a public key and you share that with the world. You just publish it anywhere. It is not a secret, but you have a secret key that you never tell anybody. See, private key encryption is based on an oxymoron. You have a secret, but then you have to tell somebody. You have this ridiculous thing called a shared secret. Well, if you told somebody else, how do you know that they didn't lose it or tell a third party? It's not really a secret anymore, is it? But you can only do it by having 2 people that share a secret, and that is an intrinsically fragile system. But this is much better. You make a secret and you never tell anybody the secret. Only one person knows the secret. That is something you can more easily maintain. Now, anybody can send you secret information using your public key, and nobody can open them except you with your private key. And it seems to me this is just like these mail slots you have in your door, right? Anybody can send you stuff by shoving it through the slot, but nobody can get it unless they have the key to open the door and get in your house. So that's the idea, that you can receive secrets with high security by making a key pair. The problem is you cannot send secrets to anybody else. They can send you messages, but you can't answer unless they have also prepared their own private public key pair. Each person has to prepare themselves to receive messages. Hello, Tariq. All right. So anyway, this happened to Ed Snowden. Ed Snowden wanted to leak military secrets from the U.S. government, and he knew that the RSA system was so strong that he could use it, but the journalists did not have RSA key pairs. And he kept trying to explain to these non-technical journalists like Glenn Greenwald how to make a key pair, and they couldn't do it. So they had to get a technical person to make the keys for them, and now a bunch of people knew the private key, and it wasn't a good system. That's the problem. This is a very strong system, but it requires technical knowledge at both ends. Exactly. 3 people can keep secret if 2 of them are dead. That's the thing. That's why public key encryption is great. You never share your secret with anybody, but the weakness is the recipient has to prepare to receive it. So this is why it is limited in that regard. Only relatively sophisticated people can talk to each other using this system. All right. So it requires on a one-way function. Many encryption systems do. So it's in principle, there is a mathematical relationship between the private key and the public key, but it should be impossible to figure out the private key from the public key. So you have to have a mathematical function that is easy to go one way, to take the private key and create a public key, but it is difficult to go the other way from a public key back to the private key. And the only difference between the public key systems is which one-way function you choose. The original one used factoring a number. Your private key was a prime number, and you multiply it by another prime number, and the product of those two is the public key, and it is a famous problem. For millennia, it's been known to be extremely difficult to factor a large number into its component primes. So that was the one-way function. Discrete logarithms are just a generalization of that to rings, which is a general set of things which can be combined to make another thing, and it's just another way to do it. And then there's elliptic curves, which use another strange transformation, which again has a hard problem, where you can make a private key and a public key. This one is the one that's really become popular because the keys are much shorter and the calculations are much faster, so it uses less time and less battery power to achieve the same level of security with elliptic curve cryptography. But RSA was the first one, and it became the standard, so a lot of people continue using it, even though it would probably be better to just switch to ECC and make your calculations simpler and faster. So the two algorithms vary greatly in the size of the keys required. A symmetric key length of 112 or 128 is strong enough that nobody can ever get in, because trying all the keys of 2 to the 112 or 2 to the 128 is more than you could ever do with all the computers in the world and all the time in the world. But asymmetric algorithms need keys that are much longer. So to achieve a sufficient security with at least 2,000 bits or 3,000 bits required, 2,048 or 3,072 bits for RSA keys. This confused me at first until I finally got it straight. The asymmetric algorithms require much longer keys, and the calculations are much more complicated than the symmetric algorithms. All right. So the NIST issues special publications from the U.S. government recommending what keys to use and under which circumstances to use them. And here's the latest version of this from just a couple of years ago. So here's their recommended key sizes. They say quit using 112. 112 is probably not strong enough, or less than 112. 112 is acceptable, but still not the best. You really should go up to 128, 192, or 256 like AES, which is why AES doesn't give you a key shorter than this. This stuff is considered to be good enough even beyond 2030. And this is another big issue with cryptography. If you encrypt something, how long will it stay secure as computers keep getting faster? You try to look in the future and see how long you can trust it to stay secure, which is why they give you this distance. And of course, the big thing they're worrying about here is quantum computers. Quantum computers are expected around 2030 or 2040, and when they get here, it will make them much faster at cracking encryption. So we'll probably have to move from AES 128 to AES 256 and abandon our current public key systems entirely and replace them with a new one when that happens. So here's more information about the comparable security strength. And you see here's 112 bits goes to 2048. And here's 128 goes to 3072. So 2048 is good enough right now up until about 2030, but you really should be moving up to 3072 or longer for RSA. And you should be aware that when quantum computers really start working around 2030 or 2040, we'll have to abandon RSA entirely. And here's their hash functions. SHA-1 is no longer recommended, and we're supposed to be using SHA-2 or SHA-3, which we'll talk about, which are considered quite strong. All right, so hash functions are just a function to combine all the bits in a file and make a fingerprint that's not very long, so you can compare that fingerprint, then transmit the file somewhere and calculate it again, and check to make sure the fingerprint is the same, and that gives you proof that the file has not been altered. So MD5 was very popular, but never actually approved by the US government for any purpose. It's not very secure. SHA-1 was considered very good, but a few years ago, Google managed to show a collision, 2 files that had the same SHA-1, which means, therefore, obviously, the SHA-1 does not prove the file is not changed. So now SHA-2 and SHA-3 are the recommended ones. SHA-2 is completely fine. There's no flaws in it that anybody knows. The problem is it's mathematically related to SHA-1, so some people are nervous that SHA-2 might be found to have a flaw, so they invented SHA-3 just as a drop-in replacement for SHA-2 in case SHA-2 is proven to be insecure someday. Almost nobody is using SHA-3 because as far as anybody can tell, SHA-2 is just fine. And there's also other ones like Havel, but it's not the official government-approved one, so it doesn't get the name SHA, Secure Hash Algorithm. Collisions are what we're talking about here in the quality of these hash functions primarily. There should be no 2 files that have the same hash. In principle, the files are longer than the hash, so there must be 2 files that hash to the same value, but they want it to be so rare that you can never find 2 files that hash to the same value in practice. But MD5 has had collisions known for a long time, and Google found a SHA-1 collision in 2017, so everyone's moving to SHA-2, and SHA-2 has no known collisions, and people have high degree of confidence that no collisions will be found any time in the reasonable future for SHA-2. The only way that would be found is if there is some mathematical flaw in SHA-2 that has not yet been discovered. All right, let's take a look at a Kahoot. Well, there it comes, okay. There we go. This is 125, 3G. Right here. All right, that might be it. I'll give it a few more seconds. All right. All right, what's the strongest system? Yep, the one-time pad is essentially perfect. except for a very serious key distribution problem. All right, which one uses no key? Hashing just puts a fingerprint on a file. There is no key. If you do repeat the calculation on the same file, you'll just get the same value. It only provides integrity, not confidentiality. All right. All right. If you encrypt 1 bit at a time, what have you got? That's a stream cipher, which has the advantage that you do not need to pad the last block to fill it up, which you have to do for block ciphers. All right. All right, which mode will preserve some patterns, which is a serious flaw. Yep, that's the electronic code book. All right, what's the weakest scheme? That's it, DES, the old one that was recommended and is no longer considered safe. The rest of them are all perfectly fine. All right, which one is popular on mobile devices? Elliptic curve, because it saves power. All right. All right, I know who that is. All right. All right, and 4D42, that's probably ASCII. Second letter is B. First letter, I don't know. They're going to tell me who they are if they want their points, though. Anyway, all right. So, let's go on here. All right, so let's talk about cryptography attacks. So the simplest one is, of course, the brute force attack, where you just try every possible key or every possible password for a password, that sort of thing. In principle, this will always work. The only problem is it might take a really long time, and there are some systems like the one-time pad where even this will not work because you will get many possible answers and there's no way to tell which one is the right answer. In most encryption schemes, however, all the wrong keys will result in gibberish and only the right key will result in readable text. Anyway, in practice, if you have 128 bits for a symmetric key or 2048 for an RSA key, then it becomes impossible in practice on current machines to ever try enough keys to crack them all. There's just too large a number of keys to try. All right. Social engineering is, of course, the best way. Attack the people, trick the people into handing over the private key somehow. This is extremely effective because people remain weak. No matter how beautiful your math is, there's always the human element. Rainbow tables are a technique of trading memory for time. And this was quite popular back in the days of Windows XP and earlier when Microsoft used an old landman hash. And it turned out that you could do most of the calculation in advance and store it in RAM. And then you could just look up hashes instead of calculating them. And so you could try a very large number of hashes very fast. And you could crack virtually every Windows XP password if you could get access to the hashed version of the password, which is why Microsoft stopped using this and moved up to the NT hashes that are much harder to crack. Known plaintext is an attack where if you know some of the plaintext, then you can try to guess the key, and there are often ways to mathematically reduce the number of possible keys quickly if you know some of the plaintext, and this is what some of the WEP cracks used. WEP being the old wireless encryption system that's almost extinct now because it turned out to not be secure. One of the many problems was that it would fall to a known plaintext attack. If you look at wireless traffic, most of the packets are very short, and they are ARP packets, and the ARP packets are mostly all the same. So you can easily find packets, and you actually know most of the bits in it, and therefore you have known plaintext. Then there's chosen plaintext. If you can actually feed data in, and it will encrypt it and let you see the encrypted data, then you can choose plaintext that might tell you something about the key easily, like all zeros or all ones, or two plaintext that only differ by 1 bit. And as you might imagine, those frequently give you some pattern in the results that makes it possible to deduce something about the key. And there's a whole series of such attacks called padding oracle attacks, where you choose something where you control the padding bits, and therefore you're able to deduce something about the result. And we cover some of them in the cryptography class. There's a whole series of attacks called Beast and Crime and other attacks involved attacking HTTPS if you can just pump in thousands and millions of carefully chosen plaintexts and get it to encrypt them for you. Meet in the middle attack is quite powerful, and this is why we have triple DES, not double DES. If you had 2 rounds of encryption with, say, different keys, then instead of trying, so you had 56 bits of DES and then another 56 bits of DES, instead of trying to crack the combined 112 bits, which would be impossible, instead you do the first half of it for all possible keys, and then you just do the backwards half by decrypting until you get the match in the middle. So you have to do 2 to the 56 twice instead of 2 to the 112 once, which means you only need to do the square root of the number of calculations. It's much faster. So having 2 rounds of encryption is no better than 1 round. You need to have 3 rounds of encryption to get it as strong as doubling the key length. That's why triple DES has a security of 2 times 56, or 112 bits. And double DES would be a total waste of time, no better than single DES. The meet in the middle and man in the middle are totally, yeah, that's right. Meet in the middle is just this mathematical trick for something you can run forward and backwards. Man in the middle refers to a privileged position on a network where you can see traffic and intercept it and modify it or read it before it goes on. So, yeah, they sound similar, but they're quite different. Man in the middle is a physical location in the network, and meet in the middle is meeting in the middle of a mathematical calculation. So if you have a calculation that can be split in half, then it becomes much easier to perform a brute force attack. Exactly. All right. So a known key, the other one, of course, is if somehow information about the key is leaking out. This happens all the time. Default passwords, the password left in RAM, the password stored on a hard disk somewhere, stored on a piece of paper you can steal, you know. If you can somehow find the key, or if the key is predictable because they based it on a dictionary word or something, then of course that makes the attacks much better. Differential cryptanalysis, I mentioned before in the chosen plaintext technique, right. If you can encrypt 2 plaintexts that differ by only 1 bit or only a couple of bits, then examining ciphertext often reveals information about the key. This was also a classified NSA secret for years, and was only reinvented after the United States government had known it for a while on the outside as a technique to break into encryption systems. Then there are side channel attacks, where you do not attack the mathematics, you attack the hardware implementation. There may be something about the way it's actually done that leaks out the key, like the time it takes to encrypt, or the power consumption, or the radio emitted by the wires, you know, something like that. Something in the hardware might give you information about the key. These are very hard to prevent. Then there are implementation attacks, where it just makes a mistake somehow, it leaves the plaintext lying around somewhere, or on the hard drive or something. Again, not a mathematical flaw, but a flaw when you actually try to build a real device doing it. And then there's the birthday attack, which is essentially the same as the meet in the middle attack, if you want to look at it that way. If you are trying to find hash collisions, and your hash is, say, 128 bits long, you might think you have to try 2 to the 128 files to find a collision, but in fact you only have to try 2 to the 64 files, which is a much smaller number, because if we have a room with 23 people, consider what's the chance of having the same birthday, just day and month, so 365 possibilities. If you have 23 people, you might think there's only 23 out of 365 chance that 2 of them would have the same birthday. But that's not true, because if you have 23 people, you have 253 pairs of people, and each pair might match. So it turns out that if your class size is 23, there are usually 2 people in the room with the same birthday. And that's the point. Hash collisions are found at half of the hash size. So MD5 will have a collision after 2 to the 64 calculations. And that's why hash functions have to be longer than this. Like SHA-1 is 160, and all modern hash collisions are at least 224. I think. Yeah, we'll get there in a minute. Anyway, so, all right. Then there's digital signatures, where you have a document and you want to sign it. So you calculate a hash, which was originally SHA-1. These days you probably should use SHA-2. Calculate the hash. Then you encrypt that with your private key. And that's a digital signature. Now, this is attached to the file, and it does not provide confidentiality. This is something like a public record, like a mortgage agreement, and you're just trying to sign it. You're not trying to hide it. You're trying to put a signature on it that nobody else can forge, and nobody else has your private key. This, in the Digital Millennium and Copyright Act of 1998, this was specified to have the same legal force as a signature with a pen. So it was now possible to do financial transactions over the internet. That's what this provides. Authentication, integrity, and non-repudiation, but not confidentiality. You know who signed it, you know it has not been altered, and they cannot deny later that they signed it, but it does not make it confidential. The main message is still there in plain text. So to verify it, you take the message, calculate the SHA-1, and then you take the digital signature and decrypt it with the public key, and prove that these 2 match. And anybody can do this with the public message and with your known public key, which is available to anyone. All right, then there's message authentication codes, which do a hash, and they also mix in a shared secret, so it proves both that the message has not been altered and that you know who wrote it. And this is used a lot by financial transactions, CBC MAC, for example. HMAC is another one, another type of MAC using a shared secret and a hashing algorithm. There might be MD5 or SHA-1 or another one. Another way to just put an integrity mark on a document so that you know who created it and you know it has not been altered. Now, the public key infrastructure is what holds all those public keys. This is a group of servers that manage digital certificates, and these are what's used to identify who you're talking to on the internet. So when you talk to Google, you use the PKI to see if the certificate is really from Google or someone posing to be Google. So you have certificate authorities are the companies that issue these certificates. They sell them to people. Then you have registration authorities and people that certificate holders sign the documents, clients like your browser that validate the signatures, and repositories that hold the revocation lists, which are signatures that have been compromised and are now considered invalid. This is an old system. The newer system replacing it is the Online Certificate Status Protocol, which does the same job of enabling you to see if a certificate has been revoked. So the private keys have to be protected. You have to back up a private key. Now, how do you back up a secret without leaking it? Didn't Russia create their own CA? They did. They recently created their own CA. And you could say it's to spy on their people. Another statement is it's so they can still view internet pages now that the whole world is blocking their access to the other CAs. But yeah, Russia is trying to create their own private internet now. If they're going to be blocked off the other internet, they want to have their own private internet. And they'll have to have their own private CA then. Yeah. Now, one thing about it is the CA is only works if it's hard-coded into your browser to trust it. So Russia can make their own CA. Anybody can. But nobody's browser will trust it unless they have manually added that CA in. So if a user outside Russia went to something signed by the CA, they would get a warning saying this is signed by an unknown, untrusted provider. So if you back up a key, you can give it to somebody to hold on to, and that's an escrow. Just like you put money in an escrow account. I used to work at an escrow agency. They hold money for other people. You can hold a key there. And if you really want to be secure, you only put like part of the key at one escrow and another part of the key at another escrow, so neither of those escrow agents can get in your stuff. All right. So SSL was the system invented by Netscape to provide encryption on the internet, which was not there in the original version. And that went through a couple versions and has now all been obsolete. Now it's using transport layer security as the new system that works the same way. So when you try to connect to a server, you do synac to open port 443 on the server. Then you send a client hello telling you what you are. I am Internet Explorer, this version. I can speak these types of encryption. Then the server sends you a hello. Then the server sends you a certificate. Then you send the certificate off to a trusted third party to verify that it really is who they say they are. And then you exchange a key, having agreed on an encryption technique, which the client can handle and which the server finds acceptable. And finally, after you exchange these keys, now you encrypt all your data with the key you've agreed on, or really with an AES random key which you transmitted using the public key you agreed on. So IPSec is an encryption routine intended to go with IP version 6, but it's available for VPNs and other use now. It's got authentication headers and encapsulated security payload. It is very complicated. It's never been completely thoroughly mathematically analyzed because it's so complicated. It uses ISACamp for key management and another protocol called IKE for key exchange. The authentication header is a header format available acting like a digital signature for each block of data. And then it has encapsulated security payload to encrypt the contents. It creates a security association between two computers to send data one way, and then a separate security association to send the return data. And so that's what ISACamp does, is manage the security association creation process. Tunnel mode is one technique that encrypts the entire packet in ESP and tunnel mode, which is probably the best one to use. There is a transport mode that encrypts data but not the headers, and Bruce Schneier, famous cryptographer, said, in retrospect, you should just get rid of transport mode. Why would anybody use anything other than tunnel mode? That's why this thing is very complicated, far more complicated than it really needs to be. But it is a standard, and it's considered quite secure, and it's used by quite a few virtual private networks these days. All right, so Internet Key Exchange can use a variety of algorithms like AES or SHA-1. Anyway, that's the joy of IPSec. All right, so Pretty Good Privacy is an email system written by Phil Zimmerman, and he published it in an open forum so the whole world could get it in 1991, when the export of encryption was still forbidden from the United States, and he got in a world of trouble for years fighting with the U.S. government that wanted to prosecute him for publishing this code. And I remember I was trying to do the same thing in the early 80s. There was a very seminal paper in 79 that published public key encryption, and I thought it was wonderful. And I said everybody should have this, and I tried to write code that would do it, but I only had an 8-bit processor, and it was really miserable, and I did not succeed. And if I had succeeded, I would have just bought myself a decade of legal trouble. How does port forwarding work in tunneling? Well, it's a problem. Port forwarding breaks a lot of protocols. So in fact, that's the problem with these tunneling. That's why I say the logical use of this stuff is a VPN, where you send all your data to another server, and then it becomes the origin of everything from that point on. So there's like two separate hops, which is how you deal, I think, with port forwarding. But yes, if you wanted to directly have IPsec traffic coming directly in you from the original source, it would be hard to set up. Yeah. All right. Anyway, he also wanted this to be free for everyone to use. So it did not use those certificate authorities where everybody has to buy the certificates. Instead, it used a web of trust where you would carry like a floppy disk or something to a key signing party, and you would now sign the keys of people you know, and then they would get other people to sign them, so you would believe this is really that person if it was signed by the friend of a friend or the friend of a friend of a friend. That was their system, which is pretty strange and doesn't scale to the internet and is one of the main weak parts of this system. Then there's MIME. MIME just allows you to send foreign characters and digital and binary information like images in email. So it's just a way, email is an ASCII text only protocol. So if you want to send like a JPEG, you can't. You have to encode it in ASCII text with something like base 64, and that's what MIME does. Secure MIME uses the public key infrastructure to encrypt and authenticate MIME-sended emails. This is how you send secure attachments to email messages. And then there's escrowed encryption. This is where a third-party organization holds a copy of your pair, and this is way you can allow law enforcement to have some access to the key. There are many systems here available, designed, although not used in America yet. There are many times the FBI is constantly trying to pass a law that would require the government to have every private key so they can read everything. That has never passed yet, but they keep trying. And there are systems designed but not implemented yet where the government would have an escrowed copy of your private key. The Clipper chip was the escrowed encryption standard announced by the U.S. government in 93. They wanted to force everyone to use this. It was abandoned in 96. There was a huge argument against it. They also at this time wanted to put the V chip in televisions to block violence and porn on televisions. It was a big deal to put hardware devices for security controlled by the government at that time. These did not succeed. As you can imagine, there was a big uproar by the American citizens saying that the government shouldn't have the right to do this, and they did in fact eventually abandon it. And then, someone asked earlier, we're talking about steganography. This is not encryption. It's where you just hide extra data inside a file. One use of it is watermarks. If you download something like a copy of a textbook, they will put a watermark in the file so they can tell who that was licensed to, and if you put it on BitTorrent and let other people copy it, they can tell who leaked it. What's my opinion about keystroke dynamics as a way of eliminating passwords? People have talked about it, using your pattern of typing as a biometric authentication scheme. From what I've heard, it's not very secure, and it hasn't really caught on. The ones that have caught on are, of course, Apple face recognition and thumbprint recognition on Apple devices. Voice print is one that sounds good, but turns out not to work very well at all. And there's other ones like iris geometry that are good, but the equipment is too expensive. So there's a bunch, they're all biometrics. The fundamental problem with all biometrics is if your key leaks, you can't change it. Can I talk about asymmetric encryption to transport symmetric key? Yeah, that's easy. See, what happens is I didn't understand this at first. If you're going to use RSA, you're going to have a prime number and the other person's going to have a prime number and you trade public keys. You can now send data the way Edward Snowden tried to, with this prime number encryption with great security. And that would be fine. The only problem is public key encryption is so complicated that it's very slow. It's very complicated to do the math. So if you were to try to upload a file to like Gmail, logging in with just public key encryption, it would take a long time to go up. So what you do is you exchange the public keys and make it and verify the certificate, and now you can send data encrypted with public key encryption to the server, like Gmail. But what you do is you just make a random 128-bit AES key, and you send that through that tunnel, and then you use AES from that point on just to make it faster and cheaper. So the only thing you actually use public key encryption for is to create the secure transmission mode that you use to distribute the private key. But it's really not a fundamental mathematical reason. It's just to make it cheaper and faster. So you can send everything at line speed without having to have a powerful processor at both ends. That's all. All right. So in fact, when you use HTTPS, you're using symmetric encryption, asymmetric encryption, and hashing. That's why we learned these. You're using them all. Zero trust security. Well, zero trust security is a network design issue where you don't have a perimeter and you trust everything inside the perimeter. Instead, you don't trust anything. So even the laptops in your network, even the hard-coded servers on your network, you consider the possibility that any of those might be compromised, and you put in other layers of boundaries of trust inside your network. And that's what we're all supposed to start doing. We're recommended by the government, but in practice, nobody really knows how to do it yet. And we're just in the infancy of people trying to build products that will do that for you. So it's more of an aspirational goal than an actual practical thing you can turn on right now. But that's the idea. These are very good questions. Now let's take a look at another Kahoot. This is 3H. Yeah, firewalls going east and west as well as north and south, yeah, and some kind of test. Every time you get a request to the server, you're going to somehow test to see if you trust that machine or not. Well, I know. Wouldn't it be? That's why nobody really knows how to do it yet. All right. I'll give it a few more seconds. Aha, good. All right. All right. So what attack will defeat 2 deaths? Yeah, meet in the middle. All right. All right. What attack deduces the key from the power consumption? Yep, that's a side channel. Good. All right. What system ensures authenticity of public keys, so you know who the public key belongs to? That's the PKI, the public key infrastructure. All right. And what system uses AH and ESP? IPSec, the most complicated one. Almost nobody understands it all. All right, David. All right. All right, and that's a 2-time winner. All right, I'm going to stop this recording.